and welcome to the Junior Engineer Summer STEM Experience hosted here at the University of Hawaii at Manoa by the College of Engineering. My name is Rayami Arellano, and I am a junior majoring in mechanical engineering.
My name is Noah Hu, and I'm an electrical engineering majoring.
My name is Ethan Kang. I'm a sophomore majoring in computer engineering.
And we are the engineering student ambassadors for the College of Engineering. In addition to planning and running Jesse this summer, we engage in STEM outreach to K-12 students and work with industry partners by planning and coordinating events throughout the year. So what is Jesse? Jesse is a 6-week program for high school seniors or rising high school seniors, and throughout this program, interns engage in hands-on engineering projects and research, allowing them to experience what engineering has to offer through real-world applications. Through this program, interns have the opportunity to network with real engineering professionals as well as college students. And this program also allows interns to transition from high school to college.
So to recap the various activities that the interns took part in, we broke it down into 3 sections. During the first week of the Jesse program, the interns first attended a campus info session and tour run by the admissions office, where they got to just go around this college and learn more about what Manoa has to offer. In addition to the campus tour, later that day, the interns spent part of their day at Alo'i and learn about the indigenous Hawaiian knowledge and plants, as well as natural resource management and food production. And lastly, the interns participated in an egg drop with last year's Jesse cohort, where they collaborated with past interns and tried not to make their eggs break when they drop it off the 4th floor of Holmes Hall. After week 1, the interns participated in various professional development workshops. First, they had a presentation workshop where all the interns created presentations and they were given feedback as well as feedback on their presentation skills. Next, they had the NHPOL workshop, which stands for Native Hawaiian Place of Learning. The interns learned an oli and performed it. And lastly, we held a resume and LinkedIn workshop hosted by the Manoa Career Center. During the workshop, students received help and tips on how to create LinkedIn accounts as well as resumes.
Lastly, interns got to participate in 7 different site visits to Port Hall Naval Shipyard, Train Technologies, Burns and McDonnell, SSFM, Booz Allen Hamilton, Kai Hawaii, and lastly, Niagara Pacific. Not only do these site visits allow interns to interact with real engineering professionals, but they got to learn about various different engineering companies and what they work on. They even got to do hands-on activities such as boat making, spaghetti towers, networking, and a game of life at SSFM. Now we would like to acknowledge the following people: Dean Brennan Morioka, Assistant Dean Zong Choi, Kimberly Perez Holtz, Ensign staff, industry partners, Naomi Eric Corian, NHPOL workshop staff, the Jesse parents and families, as well as the interns themselves. Thank you, and now we'll move on to the interns and the first round, which is the gold round.
Hello, my name is Emily Kirishima from Athens High School.
My name is Crystal Lee from Kalani High School. We're from the Robotic Space Exploration Lab, and this is the, or ROSE, and this is the ROSE Rover Project. So we're first going to talk about the lab overview with their goals and the members a part of it, and then we'll talk about what me and Emily worked on and our project throughout the last 6 weeks. And then we'll go through a day-to-day in the lab, and then finally we'll talk about the results and the summary of this project.
In this next section, we'll introduce our mentors, go over the rovers we worked on, and introduce our lab goals. Dr. Francis Zhu was our principal investigator, and And our main mentors were River, Safira, and Jack.
So one main goal for Rose Lab is their machine learning models. So they develop machine learning to look for precious resources in a certain environment, and they collect data on how the wheels move in soft soils. And the Rose Lab also participates in the University Rover Challenge, which is a leading robotics competition for college students, and they had the opportunity of going to Utah for the first time this summer.
In our lab, we work with two main rovers. The mobility rover, which you can see in yellow, its goal was to collect data on how the wheels move on the rover, compared with softer ground like sand compared to harder surfaces, and see the difference in distance it moves. We also worked on the active learning rover, which you can see in pink. Its goal was to use machine learning to determine the location of precious resources.
So now we're going to talk about the project that me and Emily worked on. So the main goals of our project was to design the rovers on CAD and then build so that we could then field test at Calaco Beach. And at the bottom left, you can see our final CAD design, and then right next to it is me and Emily building the actual rover. So the key objectives of this project was the design and fabrication of the rovers, so that there would be no complications during the actual field testing. So the importance of the mobility rover is to create a data set comparing the ground truth to the local field testing to send to researchers so that they could use our data in their own projects. The mobility rover was especially important because when the rover is on the moon or on a different planet, we're not able to pick it up if it falls down or follow it around to see where it goes. And the importance of the active learning rover was to use and develop machine learning to generate a model of the distribution of resources in a given area so that when searching for the resources, it would be a lot faster.
Some of the main projects I worked on was creating a lowering system for the awning box. The awning box was an extension of the spectrometer, and its job was to use light waves to reflect off of certain resources so that we could determine what they were. I also helped with creating a lot of the CAD, converting the electronics in the lab to CAD to better organize the rover. I also worked on creating custom pieces like the rover panels as well as one of the motor mounts for the wheels.
So for the active learning rover, I mainly focused on the electrical design. So I CAD'd most of the electrical components like the roboclods and the protoboards. And then I also designed the electrical box to house all of these electronics with space for wires and grommets. And grommets are these circles that fit wires so that wires could go through the box, but debris and dust wouldn't get in. And for the mobility rover, I worked on the entry and exit fans for cooling down the batteries in the middle. And I worked on the different mountings for these fans. I also worked on arranging all the electronics on the mobility rover. And then me and Emily both worked on the rover assembly, building the chassis.
In this next section, we'll talk about the day-to-day in our lab. The first and second week of our lab was used for tutorials and learning what we needed to know to complete our objectives. So we went through a lot of CAD tutorials. CAD stands for computer-aided design and allows you to design things on the computer. So we went through tutorials on Onshape. We also went through ROS2 tutorials, which is a programming software that the industry uses to robotics industry uses to program rollouts. So you can see in the blue square, the lines are where the rover will be moving.
So weeks 3 and 4, our main focus was the active learning rover. So I focused more on the electronics and Emily with the awning box. So for the electronics, you can see at the top middle, we started off with just an electrical box with no way to close it and 2 big window panels. And then right next to it is the current design where we incorporated just 1 big window so that we could have latches on the side and grommets in the middle. Me and Emily both worked on converting the different components to CAD, like the spectrometer and the batteries, the different grommets, and the electrical components.
Week 5 and 6 was mainly used to finalize our design for our rovers. So as you can see, we actually started fabricating the rover chassis. This week was cutting and measuring and cutting the grommets using a chop saw. And we also started putting together motor mounts for the wheels.
Week 5 was also the week that we found out that the spectrometer was we were no longer able to use it. So we had to come up with a whole new mechanism to mimic what the spectrometer did. So instead of using the spectrometer, which Emily said before uses light to analyze different materials, we used a probe which measured the moisture levels in soft soils completely autonomously. We also worked on resizing the chassis so that the fans could mount directly onto the side panels. So for the chassis, we first started by disassembling the old rovers so that we could gather different parts like the corner brackets and aluminum channels. And then we used the chop saw to measure and cut the metals. And in the video, you can see us safely cutting these metals to the size in the CAD. And then at the bottom right is the final chassis that we put together.
Some of the skills we learned in our lab were collaboration, communication, and time management. So in our lab, it was crucial that we communicated with our lab, other lab members to efficiently complete designs and work through problems. Other skills that we learned were logical thinking, redesigning, and problem solving. Redesigning was a big part of our lab since their issues popped up and we had to change and be flexible with changing the design. Some of the issues that we ran into during the lab was first, getting through the learning curve of doing new things. It was both me and Chris's first time working with CAD and programming, so getting through the first 2 weeks was pretty challenging. The spectrometer, like Chris said before, we were unable to use it and had to switch to using a probe, which was a lot less accurate and less with our design. So right now we're in the stages of redesigning a lowering mechanism for it. And it also pushed back the field testing dates that we had planned set for this week Monday is now pushed back to next week Friday.
So for the future goals for Rose, they plan on finishing the mobility rover and active learning rover design on CAD, and then they'll finish building both rovers. And for field testing, since this internship ended so early, me and Emily still decided that we wanted to accompany them to their field test to see how these rovers work.
Lastly, we'd like to share some acknowledgements and thank yous. Thank you to the UH College of Engineering and Jesse staff and faculty for providing us with this opportunity to be here, as well as our lab mentors, assistants, and fellow interns for making our experience here so memorable. Thank you for your time for today. Are there any questions?
All right, thank you, Rose Lab. Next up, we will have the Hawaii Corrosion Lab. Please come up.
Good afternoon, everybody. My name is Daniel Shiraki, and I go to Kalani High School.
I'm Brennan Lau from Hawaii Baptist Academy.
And over the Jesse program, we were partnered with the Hawaii Corrosion Lab, and our main experiment was with chloride candles.
So these are the people in our research lab. The person on the left is our principal investigator, Dr. Lord Ihara. The person in the middle is Blake Yamamoto, our mentor. And the person on the right is Ryan Tsukamoto, our other mentor.
So what is corrosion? Corrosion is an electrochemical process in which metals break down due to corrosion. So we often don't think of it as much of a big problem as it is. Corrosion costs around $276 billion annually, and in just the US alone, and $2.5 trillion globally. You may wonder where these costs come from, and if you think about maybe the last time you've seen the news and there was news about a water main break, that is due to corrosion. Like the picture on the right, it is due to the pipe corroding out, causing that water main break. Along with just that, if you think about, we live in Hawaii where the Navy is really prevalent, when they dock their ships, they're not only refueling, they're also checking for damages that corrosion could have caused the ship. Which is why it's important for us to be able to characterize and understand what type of corrosion would happen to its specific metals we put out in the field. Which is why we have
Test tracks. So these test tracks are utilized to assess the rate of corrosion within a specific environment. And on these test tracks are coupons composed of various different metals. As you can see at the right arrow, those are metal coupons given to us by the Navy to test different armors. And as you can see on the yellow arrow, those are metal cables given to us by HECO to test. And these coupons are weighed before and after to measure how much corrosion has taken place. And these test racks are placed all over the island and internationally in various different climates.
So on the test tracks, an array of sensors are placed, one of them being the chloride candle, which our experiment was mainly about. So on the picture on the right, that's an example of a wet chloride candle, which we typically place out, and the picture on the left is a dry chloride candle. Despite the name of it being called a candle, it doesn't actually burn, but the way it works is it absorbs the airborne molecules, a lot of times chloride, and it absorbs it, which we can figure out how much chloride is in a specific area. The reason why we look for chloride specifically is because chloride speeds up the rate at which many metals corrode, which is why we have chloride candles out on the test tracks.
So the goal of our lab was to identify the point at which the chloride candle becomes fully saturated. As you can see on the image on the left is a picture of a fully dry, untouched chloride candle. The picture on the right is a fully saturated candle with visible crystal growth. So the reason why it is so important to find at what point the chloride candle becomes fully saturated is because our research lab has international and local candles. So internationally, the candles can only be accessed once a year, whereas the local candles can be accessed once a month. And the international candles are usually dry candles. And the local candles are usually wet candles. And so our researchers want to find out at what point does the candles vary. So how to differentiate or how to compare them.
So this is the main procedure of our lab. So the picture in the middle is the wind tunnel that most of our experiment was conducted. So at the very end where the giant red arrow is pointing, that's where we would place our chloride candle, and we would spray it with ASTM seawater. The reason why I use a wind tunnel is because we need to give the candle even coating, so as much of it is coated as possible. So the reason why we use ASTM seawater is because it is a standardized solution, and for our case, that means that we know how much grams of chloride is in each liter. That allows us to calculate that about 3.3 grams of the ASTM seawater being deposited on the candle would be equivalent to about 1 month left out at the Dillingham Airfield Test Site. The reason why we are comparing it to the Dillingham Airfield Test Site is because that is where a lot of our researchers' chloride candle experiments are done. So after a little bit of research on our part, we figured out that about 1 minute of it being sprayed in the wind tunnel would equate to around 3.3 grams of that ASTM seawater being deposited. We have 4 different dose amounts. being 1, 2, 6, and 12 months of it being left out on the field. So the way we would do it is you would spray it for 1 minute, which would equate to 1 month, which would equate it to being left out for 1 month, and then we would let it dry overnight. And depending on how long it was supposed to be left out, for example, if it was 6 months, we'd repeat that 6 times. Once we were finished with how long it was supposed to be, we would bottle it up, similar to the picture on the right, to keep it sterile for analysis.
So some problems we ran into while doing this experiment was that our nozzles would keep clogging. And this would vary our spray times. So while we're aiming for 3.3 grams deposited on the candle, the nozzles would clog. So sometimes you would get 1 gram deposited. And to fix this, we found it best to put the nozzle in an ultrasonic cleaner and to flush the whole system with pure water. Some other problems we ran into was human error. So sometimes one person would not be watching the experiment closely enough and maybe not press the timer or start it or end it on time. Sometimes the intake to the salt water would come out of the bottle, messing up our experiment. So that was our problem. To fix this, we made a procedure to prevent these things from happening. Another problem we had was that before, as you can see on the picture on the left, our nozzle would just dangle from a hole in the wind tunnel, and this would allow the nozzle to twist and turn, preventing our chloride candle from being sprayed properly. And to fix this, we drilled a hole in the wind tunnel, and we clamped it down with a bolt.
So this is the results from our experiment. So the y-axis is the deposition rate. That basically equates to how much grams of chloride is deposited on the candle every single day. The x-axis is in months. So the red line is the Dillingham Airfield test site, and that's the real-world data that we're trying to kind of see if the dry candle that we were testing with equates to. So as you can see, it kind of starts high and it starts to drop as you go farther, as you move it out farther. And if we're trying to compare that to the blue experiment data that we got, the 1, 2, and 6 months kind of follow that same slope. But if you look at the very end, the 12 months jumps back to being around where it was, where it started. We don't think that it's because the dry candle is different than the ones that we're leaving out, but we think that it's likely due to experiment error. For example, the 12 month, we're expecting around 40 grams of ASTM seawater or less to be deposited on it, but we ended up with around 43 to 45 grams. So our researchers would likely need to revisit at least a 12-month sample to see if our hypothesis that it follows the same trajectory is true.
So a side project that we worked on was the time of wetness sensors. So our researchers have data on the square sensor, but not enough on the leaf-shaped sensor. So they gave us this job to test both sensors. So we 3D printed and CAD'd the time of wetness stand to hold both sensors at a 30-degree angle, and so that they can fit inside the wind tunnel that we tested in. We tested both sensors in the wind tunnel, and we found that salt is being hygroscopic, which means that it absorbs moisture from the air to mess with data from both sensors.
So the graph on the right-hand side is the leaf sensor, and that's the main one I kind of focus on. So the giant red arrow points to when we first sprayed with the ASTM seawater, and as you can see, after it's initially sprayed, the dry point is a little bit higher than what it was previously. Same thing to the rectangle sensor. And we can kind of figure out, as Brendan said, soap is hygroscopic, which means that it absorbs the water in the air and it kind of builds up on the sensor. So even after, with the green arrow, when we spray it with kind of nanoclear water, which is equivalent to rainwater, it still has that high, it still is a little bit higher than what it was before. So this kind of tells us data that the leaf sensor kind of behaves kind of similarly to the rectangle sensor, where soap both affects its readings.
So we want to acknowledge Catherine, our water resources researcher, who analyzed our data And we also want to thank our ESAs and the College of Engineering staff. Thank you for listening. Any questions?
Alright, thank you, Corrosion Lab. Next up, we will have our geotechnical testing laboratory. So could this group please come up?
Hi everyone, my name is Olivia Hirayama and I go to Kamehameha School's Kapala.
My name is Brandon Hashimoto, and I go to Roosevelt High School.
And this is our Jesse Lab experience. We are part of the geotechnical testing laboratory. So first we're going to go over what our lab is about, as well as some basic geotechnical terminology. We'll give you an insight as to what tests and analysis we ran, as well as our results, and close out with a few remarks. So first, our laboratory overview. The name of our lab is the Geotechnical Testing Laboratory, and our overseeing faculty was Dr. Lee, and this is our mentor, Mohammed.
So our overall laboratory's project was investigating the potential causes of distress and damage in the pavement at Qualified Parkway. And then our specific lab focused on classifying the types of soil at Qualified Parkway.
So some basic geotechnical terminology. First is the types of soil. First is cohesive soil, which is fine-grained soil, such as silt and clay. And this is determined by the size of the grain size of the soil being smaller than 0.075 millimeters. And the next is cohesionless soil, which is coarse-grained soil, such as gravel and sand. And this is greater than 0.075 millimeters.
So soil has three phases: solid, water, and air. Water and air are considered voids within soil. As you can see on the picture on the right, you can see all the three phases combined and then separated on the furthest right picture. So saturated soil, within the saturated soil, all the voids are water, and in unsaturated soil, all the voids are considered water and air.
So in the diagram above, this is an example of soil in a saturated state. So this is a glass cylinder with a load valve and piston on top, and some water and soil and a spring wheel. So the piston valve, as well as the excess weight, such as, also known as the load, this is considered excessive or water pressure, or PWP, and the water and soil, as well as the spring, is considered effective stress. So to determine the total stress, we add up the excessive PWP and the effective stress.
So there's two types of compression. The first one being consolidation, which is eliminating water over a certain period of time, or in geotechnical terms, dissipating all the excess water pressure. And then there's compaction. Compaction is instantaneously removing all of the air voids. As you can see from this example of the Leaning Tower of Pisa, the Leaning Tower of Pisa underwent consolidation at first, which is why it's tilting now. But now that all the excess water pressure has dissipated, it's going to stay stationary.
So here are some of the tests and analysis we performed.
Our first analysis was the moisture content analysis. So moisture content is the percent of water mass to soil mass within a sample. So first of all, we have to put it in a moisture can and then take the weight of that moisture can to get our wet soil. And then we have to leave it overnight in the oven in the top right, so to get the dry soil mass. And then after we put it into this formula to get our moisture content.
So these are the Atterberg limits. The Atterberg limits measures the consistency of the soil based on, and this is determined by understanding the moisture contained in each soil. So the first limit we found was the plastic limit, which can be determined when you're no longer able to remold the soil without it crumbling or cracking. And the next limit we found was the liquid limit, which is the point in which the soil begins to behave like a liquid. So our first test is the liquid limit test. And the point of this is to determine the liquid limit. We use the Casa-Grande liquid limit device. And in the next slide, you will see how this test works. But basically, the brass cup, as shown, is filled with moist soil, and we create a groove down the center. And so this brass cup raises to a measured height and falls to strike the platform below. And we count how many times the cup strikes the platform before the soil on both sides meet in the middle. And with this data, we can determine the liquid limit. So as you can see here, the brass cup is racing to that measured height and dropping to strike the platform. And the two sides of soil are slowly coming together to meet in the middle. And when they do meet is when we stop the test. So the result of this was that we found that the liquid limit was 49.84, which means that it would either contain kaolinite or fluoride. In our experience, this test involved a lot of trial and error as it was the first test we performed. And so we learned a lot about the procedures of all the tests we would be doing moving forward from this test.
Our next test we conducted was the plastic limit test. For the plastic limit test, the purpose is to determine what point the soil behaved like a plastic. So the tools we used for this test were our hands. We had to roll up our soil samples into little 3.2 millimeter cylinders. And the bottom two tools you see on the left is to measure the diameter of our sample. On the right was just a reference piece. It was already a cylinder that was 3.2 millimeters. So the results for this test was our plastic limit was around 25.455. This reinforces our liquid limit results, that our samples contain minerals of kaolinite. Our experience with this test that we had to be adaptable, as at first, when the soil kept breaking, we assumed that this was a bad thing. However, eventually we learned that this was a good thing, and that means our soil is reaching its plastic limit.
So next is the grain size distribution by sieve analysis. And this is where we determine the grain size using these tools called sieves. The sieves determine the grain size based on its number, and the higher the sieve number, the smaller the grain size it sorts out. And so what we do is we stack these sieves on top of each other with the largest grain size on top and the smallest on the bottom. And in the video you see here is us sifting through the soil using water. And the reason why we sift through the soil when it's wet is because soil in Hawaii contains a mineral called halazite, which changes material when it reaches an extreme temperature. And so to maintain the material of the soil, we had to sieve through it when it was wet. And the result of this was that our cumulative percent of soil retained was 4.61%. And we will be combining this data with our hydrometer test, which we will be showing next. This test in particular was a little more fun for us as there was less room for error when it came to performing the test. However, the calculations did prove to be slightly more tedious.
Our next test is the hydrometer test. So for the hydrometer test, as you can see in the video on the right, we have to put the hydrometer inside the soil mixture and then look at the mark to determine our reading. This test, it determines what the size of everything that fell through our sieve analysis. It determines the size of those particles. So the tools we used was the hydrometer, this picture on the left, and then we placed it into our soil sample, which is the picture in the middle. So then for the results for this test, we combined it with the sieve analysis. In combination with the sieve analysis, we resulted in this graph, which compares the grain size to the percent finer. And then our experience with this test that required a lot of accuracy and it was very time consuming, as this test had to be read in intervals of 15 seconds to 30 seconds to 60 seconds to 2 minutes to 4 minutes, etc., all the way up to 48 hours. So we had to get these time measurements very precise as well as get the 48-hour reading.
So next is the specific gravity of soil solids analysis. And the purpose of this was to measure the specific gravity, which is a measure of density, a measure of the density of a substance and compared to the density of water. And we used the de-aerator device for this to vacuum the air out of the soil, water, and chemical mixture that we made. And air bubbles out of the mixture that we made. And pre-programming our calculations for this test would be very useful.
So for a specific surface area, this was our final test we conducted. The definition is the area or unit mass of the soil, and the purpose of this test was to find the surface area, which also helped classify the types of minerals inside of it. So the tools you used for this test was the mortar and pestle. We had to ground up our soil sample as well as our calcium chloride to eventually mix together. So after that, we had to get 1 gram of our soil sample and combine it with our chemical mixture. After that, we had to put it inside the vacuum sealed desiccator, which is indicated on the bottom. So our specific surface area test found that it does not support our liquid limit or plastic limit results. So this indicates that we have to do further tests or further verification to help identify what type of mineral is inside of our soil. And then our experience with this test was very tedious, as we had to measure specifically 1 gram of soil, which is kind of annoying. And then we had to do DIY. We had to figure out how to make these 1 millimeter or 2 millimeter size lids on the bottom. We had to make this ourselves as we didn't have the available resources for it. So for specific classification of soils, we use 3 different types of classifications. The first one is the American Association of State Transportation Highway Officials. So this classification shows that our soil was A76, indicated on that table and indicated on this graph when you compare the liquid limit to plasticity index. The next one we used was Unified Soil Classification System. As you can see from where that star is, our soil falls into the CL or OL. So our soil is CL clay. And then for the Casa Grande classification system, unfortunately our soil doesn't fall in between anything, which means that our test might have been flawed, so we would have to redo these tests to get full verification of our soil.
So in summary, we enjoyed that this lab was very hands-on and we performed our own tests, collected our own data, and did our own calculations. This led us to develop an analytical mindset as not just go through the procedure, but to understand the why behind what we were doing. And all of our tests took a lot of patience, as it was the first time we were performing them, and it was very rewarding. So we'd just like to acknowledge the University of Hawaii College of Engineering, as well as the Jesse internship faculty, and our mentor. If you have questions.
Alright, thank you, Geotechnical. Next up, we will have AMMI.
Hi everyone, my name is Tate Salto and I'm from Kaiser High School.
My name is Ami Okimoto and I'm from Giolani.
And have you ever thought about the implications on this medical device economy today? Throughout the 6 weeks, we've been trying to answer this question. Welcome to the design and development of prostate models, including 3D arching materials, evaluating target accessibility and the tissue using robotic systems. We are part of the AMMI lab, which stands for Advanced Materials and Medical Instruments. Here's our presentation overview. First, we're going to be covering the lab, then the applications, then our project, then the results of the project, the limitations and future work, and finally the acknowledgements. The faculty member of our lab is Dr. Cullen, with our venture being placed in. The goal of the lab is to develop smart medical instruments in order to less invasively and more precisely diagnose and treat prostate cancer. In this, we use biocompatible materials along with imaging through ultrasound and autonomous systems in order to more precisely utilize our needles. We also create mental models to emulate the properties of the human flesh. And the eventual goal of our project is to get FDA approval along with our medical instruments being used on a daily scale. Here are some statistics of remote prostate cancer in 2020. It is estimated that there will be around 15,000 new cases of prostate cancer, along with 35,000 deaths. Also, around 1 in 8 people in this lifetime will get prostate cancer. This means that around 7 of you in this room will get prostate cancer.
So one of the main aspects that our lab addresses to help diagnose and treat prostate cancer is through brachytherapy, which is a form of radiotherapy and an alternative to chemotherapy. So there are two different types of brachytherapy that can be used. One of them being a high dose rate, where there are multiple needles with radioactive tips inserted into the cancerous tissue, or a low dose rate, where you insert these little radioactive seeds around the cancerous tissue for a longer period of time. These procedures depend a lot on placement accuracy, since you don't want to have any part of the radioactive material in a non-cancerous part of your body. And the active needles come into play here because they allow for up to 30.1% less insertions, which means that the range of punctures will be a lot less and it will cause less trauma for the patient. The needles developed in our lab also help with pubic arch interference, which is when parts of the pubic arch can block off areas of the prostate that may need to be accessed for cancer treatment.
This idea is shown in the right-hand corner of your screen in the green areas that aren't accessible using normal needles.
So what are some of the differences between active needles and our conventional needles that are used today? The active needle is made up of nitinol, which is nickel and titanium, compared to stainless steel, which is what typical needles are made of. The nitinol allows for a higher pseudoelasticity, which means that the needle will have a higher range of motion as it can bend more and is more flexible. Nitinol is also corrosion resistant, which means that it is biocompatible for use in medical procedures. The needle works through these wires that are threaded through the tips of the needle, and then there are also these little grooves cut into the tips that allow for the needle to bend. The active needle will aid with trajectory issues that can happen during medical procedures, such as issues with deflection, tissue inhomogeneity, which is when the tissue may not have the same stiffness throughout, displacement issues, or when you miss your intended target, or sometimes issues can come up when your organs shift around due to physiological processes such as breathing.
In order to create medical instruments such as active needles, we use CAD, also known as computer aided design, and the medium of SolidWorks. And in order to get a basic foundation of SolidWorks, we collaboratively created a horse, as shown by my lab partner Tad. We also created pictures of medical equipment such as blocks for the test the bathtubs, motorized stage in order to utilize the bathtubs, and finally molds in order to create the bathtubs. In testing the bathroom stiffness, we first have to find a material that emulates the properties of human flesh. We found plastisol to be the best in this. However, due to problems in the lab, we get this out of gelatin. The goal of this lab was to formulate a trend line between the ratio of gelatin and the thickness of the gelatin in order to closely match the thickness of human tissue. In order to get this value, we use a nano indenter, which creates small incisions on the surface area of the bathtub, shown in the bottom right-hand corner of the screen.
So this is a graph that we created in the end from our data. Initially, we anticipated a linear trend line, so that we would be able to eventually match the gelatin ratio to properly match the stiffness of human tissue. However, you can see that it's more of a logarithmic trend line, which means that the trend line will level out in the end. So in the end, we were unable to figure out what gelatin ratio we could use to properly emulate human tissue. The first major step in our project was to use the active needle in 2D space or in a planar space. The first step was to create a mold in SolidWorks that is pictured in the upper right-hand corner with the little targets inside. We also used SolidWorks to map out a coordinate system so that we knew at what distance and position the targets were located from an arbitrary point on the box. And then from there, we knew what numbers to punch into our code so that we could move the needle. In the video up there, you can see that we used an ultrasound system to properly see where our targets were placed, since the phantom material was more opaque and we couldn't see with our bare eyes where exactly the needle was hitting. So once we successfully completed hitting targets in a planar space, we then moved on to hitting targets in 3D space, which involved using a rotational motor so that we could go forwards, backwards, and around with the needle. So the first step in this was to create a mold that simulated cubic arch interference, as you can see with those black parts in the picture up there. We also created a prostate out of gelatin, which is the blue area that you see. And while the gelatin was setting, we placed those little black beads in there as the targets that we would aim to access.
Some limitations are allowed, mostly related to the flux of the needle, due to the fact that the needle bends differently in air and gelatin. And these issues were mostly related to non-Hall returning, which means that the needle doesn't rotate on a single axis, but instead rotates like a light, which takes time to turn. There are also 3 printing errors, mostly related to the lab. And we had a lot of trouble turning the wires due to the small scale of it needed for precision. And this is a video showing the errors that we had in the lab.
You can see that it makes kind of a U-shaped turn instead of a straight path as we were planning. So part of our procedure was testing out the needle in air before we inserted it into the needle, or into the phantom, sorry. But due to gelatin being a much more stiffer and different material than air, we were unable, sometimes we encountered those errors with predicting our trajectory. We also ran into some issues with the phantoms themselves, mainly that the consistency of the gelatin would vary based on how long we left the gelatin out from the fridge for. So sometimes the gelatin would end up melting and being softer than what we anticipated, so that sometimes can cause a little bit of problems for us. There was also leakages with the molds since when we placed the mold in the fridge to properly set, sometimes the gelatin would spill out. And as we mentioned earlier, we were unable to use plastisol in the end due to some errors with the supplies.
We would like to thank the Jesse staff and GSAs, along with Blakeson, our mentor, and Malia, our NSEM intern, along with our fellow interns and our family and friends for joining us today. Thank you. Any questions?
All right, thank you, Ava Mai. Next up, we will have our Water Resources Lab. So could you please come on?
Hello everyone, good evening. We are in the Water Resources Lab. I'm Samuel Lim, I go to HPA.
And I'm Misha Leandro, and I go to Community Schools.
So this is just a general overview of our lab. Our principal investigator is Professor Benteni. Our wonderful mentor is Nazarene, she's in the crowd. And basically the goal of this lab is to determine and predict scouring depth, which we will explain in a bit, in bridges and piers, so that we can help ensure the safety and affordability of bridge design.
So what is bridge scouring? Bridge scouring is basically the process of water flowing along the bridge supports, which erodes the sediment from underneath the bridge. This process erodes the bridge supports and makes the foundation a lot weaker, which compromises its safety and structural integrity.
So, why is this important? Well, the goal of this lab is to help engineers mitigate erosion and scouring and help them develop better design in bridges, while also ensuring that the bridge is cost effective. And for Hawaii specifically, this is very important because over 1,109 bridges in Hawaii are in need of repairs, and 7% of those bridges are considered structurally deficient, which means that they can collapse at any time.
So during this lab, we observed 3 different types of piers. So one of the first that we used was circular, which is seen at the far right-hand side. And then we focused on round nose, which is in the middle, and then we moved on to sharp nose, which is on the left.
So to help us predict scouring, we had to use some input variables, and we had 2 different categories of input variables. The first one was dimensional, which basically means that our variables have units such as meters per second, and our second category was non-dimensional. And to list some of our variables, our dimensional ones, we had diameter of pier, flow depth, velocity, critical velocity, which is the velocity of the sediments in the water, and the sediment size. And what we're trying to find is scour depth.
So in order to run our lab, we used a few different programs. One of the first programs that we used was Microsoft Excel, our spreadsheets. So we used this program to help us organize the hundreds of data points that we were given, and it also helped us run our empirical equations, which we'll get into later. And then we used Google Colab, or more specifically Python. We ran these through regression model programs to basically validate the results we got from our equations. And the hopeful result of these is to be able to eliminate the use of those empirical equations and hopefully just be able to run them through code and get accurate results.
So this is basically how we predicted our data. We used what we call regression models. And what a regression model basically is something that predicts an output, in this case scouring depth, using a set of inputs, as I mentioned earlier. And the two models that we used are support vector machines, for SVM, and random forest regression.
So in order to measure for accuracy, we used a few different ways. One of the first ways we used was root mean square error, which basically just helped us to determine the magnitude of error in our results. We also used mean absolute error, which basically just compared the predicted data to the actual. And then finally, we used R-squared, which is a little bit different because it helped us determine the correlation between those predicted and actual results. Whereas if the result was closer to 1, it meant that the data explained the predictions. And if it was closer to 0, it meant that it didn't have any correlation.
So after analyzing our predictions and our data, we determined that our random forest regression model worked the best, and that worked better than our SVM, or support vector machines model. And both of those worked better than the empirical equations, which we will talk about later. And that is basically, that is what we're trying to get to have our models work better than the equations.
So for our equation, those are a few of our error results. And for circular, our best equation was 26 with Shepard et al. For sharp nose, our best was Froelich design equation, and for round nose, our best was Bunch English II.
Now for our SVM, or support vector machine model, for our circular peers, our best prediction came when we inputted certain variables. In this case, it was sediment size, flow depth, or the water level depth, and diameter of the pier. For our sharp nose pier, our best prediction came when we used all of our variables, or all our dimensional variables. And for our round nose pier, our best prediction came when we used all our non-dimensional variables. Oh, sorry. So these graphs, on the x-axis, that's our actual scour depth, or the real-world values. And on the y-axis, that is our predicted scour depth. So our goal is basically to get all of those data points on the red line. And because when the points are on the red line, that means our predicted values are the same as our actual values. So we're trying to make our predictions as accurate as possible.
So for random forest, our best for circular came when we used velocity, flow depth, and diameter of pier. For sharp nose, it came when we used all dimensional values, and for round nose, it came when we used all non-dimensional values. So for random forest, these look pretty similar to the SMF graphs, but you can see that the dots are more concentrated around this red line, which means that random forest was a more accurate program than SVM.
Now, these are some of the empirical equations that we used, as we mentioned earlier. There's a lot. We had to run all of these through spreadsheets, but we got it done.
And here's a quick look at one of the spreadsheets that we calculated all of our empirical equations on. So we had to do all of those pretty much manually.
So after doing all of that, all of our spreadsheets, data analytics, we had to interpret our data. So to interpret our data, we used Shapley, which is an AI regression or AI model that is used for interpreting or overcoming the black box nature of our model and our variables. So for our circular peers, these graphs represent which input variables were most important in predicting scour depth. So for our dimensional variables, it was pier width.
For our road nose, our most important was pier width as well.
And for our sharp nose, our most important variable was flow depth.
So while running this lab, we encountered quite a few obstacles. One of the first obstacles was just understanding all the data because initially it was really hard to understand what each of them meant and how it was really related to our experiment. And it was also difficult because in our spreadsheets we had to translate each of the data sets from metric to English and back and forth. And so it was really difficult to understand if we were doing it correctly. Another problem that we ran into was with the code because we and Sam would get different results when we ran our code. And it took a while to fix that code and make it run properly. And then finally, one of the biggest problems was actually with our hands-on model, which we'll get into next.
So, to build our hands-on model, our idea was to create like a pier and run water through it. So we will represent the idea of scouring. So in this bottom picture here, that's us going to Manoa Stream and getting dirt for our model. And in these three pictures on the left and on the top, that's us building our model. What we used was popsicle sticks. We put them together and we put clay over it. But putting that clay was a bad idea because as you can see in the right two pictures, when we took our pier out to drill a hole, our pier got really soaked and it basically melted.
So we realized that we needed to have a more structurally sound pier. So with the help of our ESA Brandon, we collected dowels and spare wood, and we were able, in the top left, that's them cutting the wood to size to fit the box. And then we also teamed up with the machine lab and Dr. Pepper, who helped us drill a hole into our box. And we met some of the other fellow UH students in the lab next to ours, who helped us cut all the dowels to the same size, and then gave us the tools to drill each of those into our pier. And then on the far right, you can see the pod we were left with last week, where we covered it in clay again just to make it look a little bit better. And then we were actually able to run this experiment just this week, and this is in my front yard. So we were able to run the water through our box to try to simulate what would happen during scouring. And on the far right, you can see the results of that were around each of the legs of the piers. You can see divots around each of them, which is basically what scouring does.
So after the 6 weeks with Jesse, we learned a lot of things, but a few of our key takeaways was that engineering has a lot of collaboration, and it's really good to meet new people because you learn a lot of things, especially going on site visits. And we also learned to not be afraid to ask for help, because in our lab we had a lot of problems with code, so luckily our mentor was there to help us. And we also needed help building our pier, and we were able to get people from the MES lab, and Brandon, our ESA, was able to help us. And we also learned that while there is a lot of innovative work in engineering, there's also a lot of hard, repetitive work that is needed to create those new innovations. In conclusion, we'd like to thank UH Manoa College of Engineering, the Engineering MES Lab, our mentor Nazarene, our wonderful ESAs, our fellow interns, and our friends and family for coming out.
Thank you. Any questions?
Alright, thank you, Water Resources. Next up, we will have our biosensing laboratory for the human body.
Good evening, everyone. My name is Juliana Shi. I'm from Yale Army School.
I'm Rakasha. I'm from Kalani High School.
Today we'll be presenting our research over the summer through the Biosensing Laboratory. Our presentation is titled Developing and Evaluating Algorithms for Heart Rate Detection via photoplethysmography sensors, otherwise known as PPG sensors, then analyzing the impact of music genres on heart rate.
So this is a brief overview of what we'll be going over with. So on the start, we have our biosensing lab overview of how the PPG sensor works, the two different algorithms that we created, the frequency domain analysis and time domain analysis, and our experiment that we conducted and our conclusions.
The lab that we were part of is called the Biosensing Lab, and as of now, their main research is focused on human physiology and stress and how those metrics change within environmental parameters.
So on the left, we have our mentor Kate, who helped guide us through the whole 6 weeks of internship. On the right, with the Professor Olga Boric-Lubeck, who gave us the lab space and the equipment to work with.
Next, a crucial part of our research involved using the PPG sensor.
So over here, we have a whole diagram of how the PPG works. So on the top left, you have your skin, veins, and everything, right? And on the green, it's your LED from the PPG sensor. So the green LED lights shine through your skin and hits your blood vessel or your pulsating radial artery, so your blood vessel. And over time, the blood vessel changes because your heart is pumping blood, so the blood volume changes from the blood vein. And what the PPG does is it shines the green LED light onto the vein, and it records how the blood vessel changes the volume over time. And it will put through a spectrometer and put out the graph over here, like over there, and show like the different wavelengths or sine waves. So it gives data such as the blood oxygen levels or heart rate, and gives out data like green count 1, 2, IR count, and red count, but mainly you're focusing on your heart rate.
So this is a sample of what the sensor outputs. Data such as the green count, IR count, and red count can be used to find heart rate.
And this is the PPG sensor that we use. It's called the health sensor band, and you can see the green LED light on it.
Like we mentioned before, the PPG sensor can be used to find heart rate. So first we will discuss method 1, frequency domain analysis.
So we start with your raw data after running the PPG sensor. So after the raw data, we put it through the bandpass filter, which will remove the unnecessary wavelengths. And after that, we put it through FFT or fast Fourier transform, which will help us find our heart rate.
Normally there are 3 types of filters, but we decided to select the bandpass filter because its frequency is between 1 to 2 hertz, making the algorithm only focus on the frequencies that we want.
So we chose the Butterworth bandpass filter because it was the most efficient for what we needed. And on top of that, it makes it the signal more flat, so it makes it more accurate when finding our heart rate.
The recorded signal is a combination of various sine wave frequencies. Then the bandpass filter minimizes the less optimal signals, helping us find heart rate easily.
And this is a GIF of how the FFT or fast Fourier transform would work on the signal. So you can see it changed from time domain, the x-axis, and changed into the frequency domain.
This is an example of the FFT being applied. The selected wavelengths from the bandpass is inputted through the FFT, which changes the wavelengths from time domain to frequency domain. This essentially changes the x-axis from time to frequency. And for reference, 1 hertz is equal to 1 beat per second.
Next, we created an alternative algorithm, which is time domain analysis.
The time domain analysis method also uses the raw data from the time versus green count graph. Then that graph is inputted through the peak-to-peak analysis, then through peak-to-peak variability, which calculates the time between 2 peaks, and then finally through the histogram, which statistically analyzes how often the participant's heart rate occurred.
So the peak-to-peak analysis basically calculates the difference between each peak and will be used in the program or help us find the heart rate. But each signal or each point is when the heart pumps the blood, so like boom, boom, boom. It's like how it is on the frequency.
And this is an example of what it looks like with our data. The interval is the y-axis and the time is the x-axis.
So after the peak-to-peak analysis, we put it through a histogram to help us find the heart rate. So on the x-axis is the time intervals, and on the y-axis is the frequency. So in each time interval, there's different amount of frequencies. And the highest point over there, you see 0.85 seconds. That's the x-axis. And we use the equation of 60 divided by highest peak x-axis equal to the heart rate or BPM. So in this case, it will be 0.85 seconds. So the 60 divided by 0.85 seconds equals to 70.58 BPM or heart rate.
To compare the two methods that we just discussed, this diagram shows the steps on how the data is processed.
And this is a graph of how it compares frequency domain analysis and time domain analysis. So it shows that frequency domain analysis is quicker, but it's not very accurate compared to time domain analysis, where there's a lower percentage error. And on the lowest row, it shows the control where we took our heart rate with a very advanced BPM monitor.
And this is us using the highly advanced Japanese heart rate and blood pressure monitor. Subject A's BPM was 68 and subject B's BPM was 83.
After creating the two different algorithms, we ran through an experiment where we recorded everyone's heart rate and how it changes by listening to different genres. And we used the time domain analysis because it was much more accurate compared to frequency domain analysis.
This is important to look into because a study done by Harvard Health states that listening to music may boost exercise ability, ease stress and anxiety, and enhance recovery from strokes. Now this shows that music can have a positive effect on someone's body, but how well can the genre of music affect someone's body? And our research focused on finding the most optimal genre to ease someone's heart rate to reduce stress and anxiety.
So this is the procedure of how we ran the experiment. So to start, we gathered 5 different people, and we gathered 6 different songs from 6 different genres. And we had the subject listen to nothing for 3 minutes while recording the heart rate, and then we let them rest for a minute, and then repeated 6 times by having them listen to a genre for 3 minutes, and then have them rest.
And this chart shows the different genres along with the songs that we use and the BPM for each of the songs.
And these are the 5 different graphs we got from the 5 different subjects listening to 6 different genres.
These tables compare the normal BPM of that participant to the BPM of each of the genres for all subjects. The red highlighted numbers show the least optimal genres as it increased heart rate instead of calming it. Conversely, the green highlighted numbers show the most optimal genres as it calmed the participant's heart rate.
There are also some outliers. For example, classical may seem to be very efficient in lowering your heart rate, but in subject D, it shows that classical really raises their heart rate. So maybe it's down, I'm not sure. And it's also shown that pop can also lower their heart rate. So for some people, it can raise their heart rate, but also for some other people, it can lower the heart rate.
In conclusion, we found that classical and jazz music were the most optimal genres as it calmed the participants' heart rate the most. However, we do have some limitations with our experiments as we only tested 5 people. So for future research, we plan to test more participants and have a larger pool of subjects.
Finally, to conclude our presentation, we would like to discuss what we gained out of this internship.
We learned a variety of skills over the past 6 weeks. This includes coding, researching, engineering, data analysis, presentation skills, and utilizing online resources.
Thank you for listening, and special thanks to the Jesse staff, New College of Engineering, Kate, fellow interns and mentors, our families, friends, viewers, and participants. Any questions? Yes.
Sorry you can't hear me, but I just wondering, since you guys had jazz and classical music as your number 1 group, I just want to ask if you guys had any speculations on why you think those maybe were most common.
I guess it's like kind of the vibe, you know, like pop is like really hyped up, but like sometimes the beats per minute in pop music is like really low. Like for example, like in espresso is like really hyped up, but the BPM is really low. But for jazz, it has a really high BPM, but the vibe is like very chill, you know. So like maybe your heart, like maybe like the way your brain processes it, you know.
And we also found that the participants who like the genre the most oftentimes had the lower heart rate. So for me personally, my most optimal genre was classical music because it lowered my heart rate by almost like 12 beats per second. So yeah, it was based on like how well we also like the music.
Any other questions? Okay, thank you.
Finally, next up, you'll have our other biosensing group come up for vitals.
Hello.
Hi everyone, I'm Jay Roki and I'm from Boyd Baptist Academy.
I'm Brianne Morello from Milani High School.
And I'm Quentin, and I'm also from Boyd Baptist Academy.
My name is Jesse. I'm from Kiwanis High School.
And today we are presenting our work at the Biosensing Vitals Lab. We'll have a brief overview of what we've been doing for the past 6 weeks, and we'll dive into some basic concepts behind our lab. We'll show you guys 2 projects that we worked on, as well as a special third project that we designed ourselves. We'll talk about some problems that we've encountered, and finally our conclusions.
So just as a quick overview of our lab, our mentors were Mohammed and Samira. The principal investigators of our lab was Dr. Olga and Dr. Victor, and we are part of the Biosensing Vitals Lab. Basically, we're looking for ways to detect a person's heart rate and respiratory rate using non-invasive and non-contact methods.
So once again, our aim was to provide a contactless way to detect a person's respiratory rate. And this is important because we might not be able to always help a patient's arm or put a sensor on somebody. And this may be true in people like newborn children who may not be comfortable with that sort of contact yet, or infected patients who it wouldn't be optimal to be in close proximity to them, or burn patients whose skin is, it's not ideal to put any sensors on their skin. And so going over the current technology, what we have is like optical infrared light cameras, or reflection LED-based type pulse sensors, or spirometers. And the problem with these things and many others is that there's limited mobility. They're very obtrusive. So as you can see that picture in the middle with that individual hooked up to all those wires and sensors. And they're also very expensive to install and work. And this is why our lab is important, and our objective is to make sure we can eliminate those problems.
All right, so the process of our lab is that we would start taking test trials at different parameters, and then we would also do data collection on those test trials. And we would accomplish this by using 2 antennas, which we'll get to later. We'll explain all of this later too. And our mechanical mover, which you can see in the picture on the right. And then our antennas use the Doppler effect. And we also use continuous waves, which is a radar type. And some other hardwares that we have are mixers, low noise amplifiers, splitters, phase shifters, and low pass filters. And so how does the antenna work? It is a 2.4 gigahertz continuous wave quadrature channel Doppler radar. So that means on the top right, you can see the 2 antennas, and then we use those to see time and range of movement using the mover on the bottom. So if you play the video, that is an example of our mover. So all it really does is move back and forth, and we can control that using a program. And it pretty much just simulates a human torso in a controlled environment.
Earlier, Quentin mentioned the Doppler effect, which is a crucial part of our lab. So the Doppler effect describes how, as an object moves, or it describes how a wave's frequency fluctuates as it hits a moving target. So as an object moves towards the source of a wave, then when the wave gets reflected back, then it'll oscillate at a higher frequency. But as an object moves away from a wave, when it gets reflected back, it'll oscillate at a lower frequency. And by studying how the frequency of a wave changes, that's how we determine how an object is moving.
So this is just a quick overview of the different softwares and technologies that we use. So one of the things that we used was VS Code. This was used to basically send out signals from the radar. And we used GDK, which basically set the amplitude and frequency of the mover. This would allow us to simulate the inhale and exhale of a human breath. And after we use both those softwares, we would go into Google Cloudatory, where we develop programs and different functions to analyze our data. So in terms of the type of wave that we use continuous waves, and basically this would make it so that there is constant power flowing through, so the amplitude and frequency would stay at a constant rate, allowing us to collect data in a more precise environment, and it's also much more cost-effective considered to other waves, and it's also very easy to analyze the post-process data.
So now we're going to move on to our first objective, which was data acquisition. And this objective included radar calibration and data taking. And we did this in 3 steps. Our first step was to just get acquainted with the radar technology. Our second step was to take data from various types of movements to prepare for human data. And our third step was to take said human data.
So the general process of collecting data is the 4 steps here. So step number 1 is to set the amplitude and frequency of our mock torso, and that was using the GDK software as discussed earlier. The second step is to run the program in VS Code. This would send out the continuous waves and allow us to collect the data. And step number 2 and 3 are kind of combined together, where we run the program in VS Code, and this would give us the I graph, the Q graph, and a graph that combines both elements, the IQ graph. Those graphs can be seen on the pictures on the right over there. And step number 4 would to be save all the files, so that way we can post-process in Google Colaboratory.
So now our first experiment was called radar calibration test. Basically, this is 26 data sets at various parameters. And the point of this was just general standard movement of the mover. So the mover would just move back and forth at a set amplitude and frequency. And it would mimic a real-life chest. And this is because we set the maximum amplitude of the mover to be 1 centimeter. And this matched the maximum human chest expansion of 1.2 centimeters. And basically the point of this step was just to acclimate us to working with the technology and getting used to the data collection process. And as you can see on the top right photo, that's us in process of taking one data set. And those 3 images on the bottom are just some of the technology that we got familiarized with. And that table on the top left is just the different variables that we set our mover to. The images below that is just all the files that we ended up taking. And the image on the right is just what one of those individual files looks like on the inside.
Before we move on to our next experiment, I'll explain a pertinent issue. So we have 2 channels called the I channel and the Q channel. They both transmit and receive radio waves. But they're phase shifted in such a way that when one channel has their optimal point, as we'll explain later, another has their null point. And also, they also have 2 different pairs of mixers and 2 different pairs of low noise amplifiers. And that causes variations in the amplitude and the phase shiftedness between the 2 samples. So if we process the 2 channels together without doing the balance correction, then we'll get an ellipse-like figure as shown in the graph above the blue part. And we want a circle. Also, there's going to be extra frequencies that we don't want. So that's why we need to do the balance correction.
So the experiment that we carried with that issue for imbalance correction was we just set them to a high peak-to-peak amplitude of 4 centimeters. And the reasoning behind this is that using a higher amplitude for our mover gives us a bigger arc. And as you can see on that image on the left, using a 0.6 centimeter amplitude for our mover gave us only a tiny portion of our arc. But using the 4 centimeter amplitude, as you can see on the right image, we get a larger, more pronounced circle. And this just gives us a larger amount of data and gives us more numbers to use to calculate the difference between those 2 channels with imbalance correction. And the good thing about this is that because it's a hardware issue, the difference between those 2 channels is constant, and we can apply it to all 4 tests.
All right, so like how Jaden mentioned before, our radar system does have null and optimum points. So that means there are certain distances that give better data than others. So in the next slide, we have our experiment, which is the step movement. And so this means that we would program our mover to go to a certain X position, and it should oscillate sinusoidally for a certain amount of time, which was like around 15 seconds, and then it would go into another X position and repeat that process. And so we wanted to do this, or we performed this experiment to see how the signal would behave at different distances. And then this was also to help find the null and optimum points.
And then our 4th experiment was just the effect of radar cross-section on radar signals. And radar cross-section is just the area that is getting reflected back to us by our signals. So it's kind of just like the size of the subject that's in front of the antennas. And what we did for this one is that we replaced the foil torso with metal spheres of 3 different radii. So those would be 5 centimeters, 7.5 centimeters, and 10.4 centimeters. And we just ran each size with the mover at 0.2 hertz and 0.5 hertz of frequency. And as you can see on the top right image, that's just what one of the spheres looks like. And looking at the graph below that, the 3 different sizes create 3 different graphs, and they're on different levels on this graph. And this basically just tells us that our signal does in fact differ when we're presented with different size subjects. And this applies to taking real data with humans because individuals aren't the same size, they aren't the same shape. So this would help create a better, robust system that can get used to the differences in people. And just to summarize all the things we did, so imbalance was just calculating the difference between the I and Q channels due to the mixers. The step movement was just to see how our signals behave at the different distances. And the metal spheres were just testing spheres at different radii to see how our the radar cross-section affects our data.
So experiment number 5 was done taking actual human data. So before this, we were doing everything based off of a mock torso. So that means we were basically simulating a computer-generated thing where we're kind of like duplicating a person inhaling and exhaling when they're breathing. So now we have an actual human subject breathing in front of the radar, so that way we can get more realistic sets of data. So in this case, on the picture over there, you can see one of our subjects sitting in front of the radar, and they're breathing at a constant rate of 14 and 15 beats per minute. This was measured using a metronome app, and basically, like I said, it allowed us to collect more realistic data, and the graphs on the bottom right is what we got.
So after we finished all of our experiments, we went into Google Colab and coded post-processing algorithms using Python. The method of post-processing that we used is called arctangent demodulation. That sounds complicated, but it's a fancy way of saying that we took our I and our Q channel signals. We graphed them on an I versus Q chart, and we took each data point, and we took the angle between the data points and the x-axis about the origin. The first step of arctangent demodulation is called circle fitting, where we literally fit a circle to our data. Next, we do DC offset computation, which means that we move our data to the origin, like in the orange data represented in the left. We do this because if we don't move the data to the origin, then you can see there's small crests and troughs in the bottom right graph. It's not a clean sine wave, and the DC offset fixes that problem. Next is unwrapping. We have to do this because the computer only takes angles between 0 and 360 degrees. So if an angle goes from 359 to 360, instead of going to 361, it would drop all the way to 1. And instead of going from 1 to 0, instead of going to -1, it would go to 369. That causes these huge drops and jumps as shown in the bottom left graph. But when we unwrap, we expand the domain of angles that can be in the computer, so we get this clean sine wave on the bottom right. Next, we did fast Fourier transform, or FFT. This is basically a check to make sure that we're doing everything right. So this converts the data into a frequency versus magnitude graph. And as you can see on the left side, this is just from our simple sinusoidal movement data. So there's just a clear peak of 0.5 hertz. But on the right, this is from our human data. So there's a lot more noise, but still you can see a clear peak around 0.2, and that is our subject reading.
Okay, for our 6th experiment, we tried to classify between locomotion and sedentary data. So I would like all of you to know that we did do this entire experiment, or we came up with the experiment process by ourselves. And so what we did was we tried to set up an experiment where the human subject, which was one of our mentors, they would move between 2 chairs while the radar is still running. So you can see on the right, we had 2 different ways to set up the chair. On the top, it was front to back, and on the bottom, it's side to side. And so why we did this was pretty much to try and see the difference between locomotion and sedentary behavior. And then we wanted to see how the movement affects the data in our charts. And we wanted to do this because most of our data was controlled or they were just sitting and not moving.
So this is kind of the matrix that we used to track our data. As you can see, we had 6 different trials, and there are 3 different variables that went into this experiment. So number 1 was the breathing rate. Again, like our previous experiment, we used a metronome app to track that. So there was 14 beats per minute and 16 beats per minute. And like Quentin said before this slide, the chairs were in either one of 2 positions. Number 1 is side to side, or number 2 is back to back. And the chairs were at various different distances, the lowest being 0.5 meters apart, and the highest being 1.5 meters apart.
So in order to differentiate between locomotion and sedentary data, first we took the entire set of data, and then we did our normal post-processing using arctangent modulation. Then we got our arctangent values, and then we segmented them into 2-second intervals. Then using each interval, we took the standard deviation, and if it was higher than a certain threshold, that meant that there's a lot of variation, meaning lots of movement, and then we would cut those out. So on the bottom, there's charts of I versus Q. On the left side of both, then there's a lot of mess, but on the right, there's more of a clean arc.
So the graph on the top represents our experiment where the big kind of spike in the middle, that's where our subject is moving from chair 1 to chair number 2. And the graph on the bottom left is basically an unfiltered graph, where all the elements come together to form one cohesive graph. So basically that's the breathing rate, that's the movement, and maybe some outside signals all into one graph. However, when we filter that graph, we get the graph on the bottom right. That one is where the movement from chair 1 to chair number 2 is filtered out, and any outside signals are also filtered out, so that way only the breathing rate is shown. So the big kind of spike towards the beginning of the graph, that's when our subject is inhaling and exhaling.
This is the results from when the subject moved from a front chair to a back chair, as opposed to the previous slide, which was when the subject moved from side to side. As you can see at the top right, this is our process graph of everything, including locomotion. As you can see, there's a big spike in the middle, which is when the subject moved. On the top right, here's our FFT of the full experiment with locomotion. As you can see, there's a lot of noise, and you can't tell how the subject is breathing. On the bottom left is our algorithm, is when we use the algorithm to cut out movement, and this was before the movement. So as you can see, there's a big peak where the subject was breathing, around 0.2 or 0.3 hertz. On the bottom right, the peak is less clear. This is because our algorithm wasn't the best, so there was still some noise left over.
And then going back to just some conclusions for this experiment, once again, our goal was just to differentiate between locomotion and sedentary behaviors in our subject using radar. And one conclusion that we found is that it does work better for the side-to-side data sets compared to the front-to-back data sets. And we think that this must be because for the front-to-back data sets, the subject would be moving from the front chair to the back chair, and they would be getting farther away from our radar, and that would possibly make some discrepancies in our data. Another point that we discovered is that there were some issues with our deviation program, cleanly cutting off the ends of the movement. That was probably because of just some imprecise calculations with our program. But mostly we found that our deviation program was more on the successful side. And just for some future works and the importance of this experiment, the reason that we did this is that because people are constantly moving, and we need to provide systems they must be robust enough to classify and be able to recognize when a subject is moving around. And in the future, we want to be able to differentiate between normal movements versus actual medical emergencies. And this is important because on our graphs, they do look quite similar, being very just erratic and messy graphs.
Okay, so some problems that we encountered within our 6 weeks in this internship would be that we would get some bad data sets or some messy graphs. So on the top right, you can see an example of a good graph, and then on the bottom, you can see Godzilla shooting a laser beam out of our graph. So that would be a good example of something that we wouldn't want But yeah, we did get a lot of those, and we would just have to work around it. And some other issues would be our mover. Sometimes we'd have a hard time starting it up, so that would take time away from us getting more data collected. And then also our distance wasn't always consistent with the mover, so that would kind of interfere with our data collection too. And lastly, there's some different torso shapes that were mentioned, like the spheres, and then our mock torso.
Here's some problems that we encountered with coding. So as we were doing circle fitting, it couldn't take in certain amplitudes below a certain point. So for example, as you can see, we have data for a 0.6 centimeter amplitude movement versus a 0.8 centimeter amplitude movement. With the 0.6 centimeter amplitude, the smaller the amplitude, the smaller the arc is on the I versus U graph. And if the arc is too small, it just looks like a straight line. So the computer interprets the circle as being way huger, as it way more big than it really is. So as you can see, the dimensions for the circle for the 0.6 centimeter amplitude are on the tens of thousands, while for the 0.8 centimeter amplitude, it's on the scale of less than 1. Also, for our locomotion experiment, like I mentioned earlier, our algorithm was unable to isolate movement for certain periods.
So in terms of takeaways and conclusions for our lab, throughout the 6-week period, we learned various different things. So number one was programming for our post-processing data and data collection. We learned how to use Python as well as some software such as VS Code and Google Collaboratory. We also learned how the Doppler effect affects different radars. We learned how human movement also affects the data that we get from radars. And we also learned the different types of graphs that are produced from our experiments. And like anyone and anything in life, there are always rooms for improvement and future iterations. And in terms of our lab, number one, we can organize our code better, so that way if someone were to continue this experiment in the future, maybe we can add more comments or define more functions to make it easier to read and use. We can also create a more precise testing environment, so this means more precise measurements between all of our elements, or maybe less noises from outside influences.
And then just some acknowledgements. So we'd like to thank the College of Engineering for giving us this opportunity, the Jesse ESAs for tolerating us throughout this entire experience, the fellow Jesse interns for motivating us and just being fun people to be around, Samira and Shadman for mentoring us throughout our lab, and our family, and you, our family and friends, for showing up to this symposium. And thank you. Any questions?
Sorry, I'm a little still confused. What is the difference between locomotion and sedentary behavior?
Good evening, everyone. We are part of the USO Connection Project. My name is Kanali Seals. I'm from Moana High School.
And my name is Kyla Canazo-Vantolino from Moanalua High School.
We are in the microwave millimeter lab. Our lab goal is to find a better way to detect UXOs in Hawaii specifically. Our mentor is Andrew Alling, and our professor is Dr. Lee Sherman.
And just a quick overview of our presentation tonight. We're going to go into some background information and what we did over these past 6 weeks, a quick conclusion, and a personal project that includes a metal detector.
Alright, so let's get started in the background. I mentioned UXOs in the title slide, but what exactly are those? UXOs stand for unexploded ordinances, which are basically bombs that did not detonate as intended. Common examples of UXOs are rockets, grenades, mortars, and even bullet casings. UXOs come from military training. Not every round fired on a military test field detonates on impact. And the military doesn't always clean up after themselves, so they usually stay in the ground. UXOs pose a huge problem in Hawaii because they obviously pose an explosive threat to surrounding communities and surrounding ecosystems.
An example of these communities is really close to home, actually, in Kahana on Oahu, where you can see this red part is where some UXOs are found. And another example is Waikane in Kaiohe. And also a major one, Waikoloa, where there is Waikoloa Village, the airport, and even Mauna Kea Beach Resort, where it's very highly populated And all these red dots you can see on the screen are UXOs that were found there.
Alright, so our problem basically is that we need to find a way to detect UXOs. Our solution was EMI, or metal detectors. Being that our project is based specifically in Hawaii, that poses a whole bunch of new nuances to our solution. In Hawaii, the basaltic rocks contain significant amounts of magnetite and other iron-containing minerals. Essentially, in some areas of Hawaii, the soil is basically a sea of iron, which makes it difficult for metal detectors to differentiate between UXOs and metallic soil.
And just a quick theory about what metal detectors do. We're going to dive into Faraday's law of induction and Maxwell's equation that helped us understand this. Basically, Faraday's law of induction is where you get a piece of metal, shown on the right, wrap it around some wire, and send an electrical current through it, or electricity, which would create a magnetic field. And the same thing can be said the opposite way, where, as you can see, the magnet is passing back and forth, where if a magnet would pass through a metal and a wire, it would create a current, or electricity.
In the context of finding UXOs, metal detectors work by sending down an electromagnetic field into the soil beneath it. This will induce a current into the possible metal or possible UXO. Then the metal detector will rescind its electromagnetic field. Then the currents in the UXO will cause the UXO to create its own electromagnetic current, which the metal detector will then detect. This will give the operator, it will result in a signal being given to the operator. It's important to note that there are a lot of variables which can affect the signal given to the operator, such as the type of metal or the orientation of the metal.
And from this, we went into our projects. And one of the problems we faced was that during work, you guys would be at your office for 8 hours a day or even longer. And the same could be said for people out in the field using metal detectors, where they're in the blazing hot sun, and they're probably getting tired, and they're just probably walking out, and when they're scanning, they might get lazy, which could tilt or mess with the data that we would collect, and that could pose a problem because funding and projects would be delayed because they would have to go out again, do it over again, and for this problem, we went and decided to go into like the gyroscope and the accelerometer. And we use this from a starter kit, which is the Arduino, and some online libraries or coding that we saw.
So as explained earlier, the different types of metals have a different, or give a different signal. We wanted to take advantage of this fact, so we decided that perhaps we could analyze the signal coming from the metal detector and find a way to differentiate between UXOs and metallic soil. We decided to collect many audio files and then catalog them with metals and their corresponding pitches.
And from this, we got the audio files with experiments. And as you guys can see in the picture on the top right hand, we went out into the field with some audio processors and a processing app called Audacity, which would help us detect the sounds that we put the metals on the ground, scan them with the metal detector, put it into this data, and then later analyze it. And this is a quick video. Here's another one.
Essentially, this is the real tangible data that we collect from our experiments. So here's the data. Here is some of the data we got and the examples of how we, analyzed it. If you look on the right side of our screen, you'll see that there is an audio track in audio processing software, Audacity, I should explain. We would input our audio file into the program, then we would highlight whichever part of the audio we would want to analyze, and then we would use the software to basically graph all of the frequencies from the metal detector along with their magnitudes. So then we would basically grab the three top most magnitude, or the 3 top frequencies with the highest magnitudes, and then we would plot it down in a graph. And then here's a quick example. We found that brass commonly has a note of D sharp, and steel has a common note of A to D. Here is a closer look at the data sheets, or how we would analyze it. Basically, you see the different frequencies and the different magnitudes. We would look at the peaks of each side, and then catalog it down. This side is brass, while the other side is steel.
And besides this, we also got to see the political side of engineering, where before we go out and test and build, you have to create a plan. These are what these meetings or politics are for. So every week, we would go with our mentor and our professor and see them talk one-on-one with different disciplines and see how they're planning out, how they're doing this project, because this is in the pre-proposal stage and they want to get funding to make this project happen. And some disciplines that you could see is electromagnetic, photometric, acoustic, and sound integration. And a lot of
So here are some of our conclusions. Throughout our 6 weeks, we faced many challenges with our 2 projects. For the first project, we entered this program with no prior coding or electronic experience. This made creating the gyroscope and accelerometer very difficult. We had to take a lot of time to get used to the equipment. Secondly, our code simply wouldn't work. Whatever computer we used, the library wouldn't download, so basically we couldn't move forward. So we decided to move on to our next project with the pitches and tones. However, in that project, we also faced more adversity, as with a lot of our sample metals, we would get something called overload from our metal detector. Basically, overload is something that happens when our metal detector gets overwhelmed with the signal coming from a piece of metal. So essentially, you can't get any data from the overload, and that made a lot of our sample pieces really useless.
And these are a few things that we learned personally from these 6 weeks. And despite engineering being known for being hands-on, technical, we also learned that it was more research-based and collaboration with different disciplines and different people that are experts wherever they are. This involves a lot of coordination, and from this, you get networking skills with different jobs, or even just anybody. This can help us with job opportunities in your future, and also we learned that site visits can help you find your future as well. And we'd like to acknowledge a few people, the UXO project members that we see weekly, Sage and Keith in our library, in our lab, the Jesse staff, fellow Jesse interns, and you, family and friends. And before you go, you presented a little song where we had metal detectors, Nina clarinet, and Kainalu on guitar.
This is basically a little side project to show that